Okay, welcome back again to lesson 2, Newton's first law. Here we're going to be doing example 2, and I forgot to write on this dash 2 because this is the second example problem on the second example of 3 examples, so there's one more to come after this. And this second example on the second example is going to be dealing with a 2D situation. So we're still finding the equilibrant like on the last one, except now the equilibrant is going to be at an angle. Dun dun dun. Don't worry, it's not too bad, and it's nothing we haven't done before. Let's choose a new color and get going on this. To set this question up, we have an object again, and this object is being pulled to the left by a force of 30 newtons, and it is being pulled down by a force of 50 newtons. So if we were to determine the net force on this object, which we have been doing before, we would draw our diagram tip to tail style, right? We would draw a 30 Newton force out to the left, and then we're going to tip to tail like we always do, okay? Tip to tail down here of 50 newtons. I'm going to label those here. So F1 is equal to 30 newtons. Force 2 is equal to 50 newtons. Okay, and our net force on this object is, turn my line tool on, down and to the left. This is our F net. Common mistake people make, right? They start drawing their net forces and they're going to draw one triangle out this way, one triangle down this way. They'll label this one 30, they'll label this one 50. You can't do that. I see this so often. Please don't get caught by this. This is one of the most common mistakes, and your magnitude will be correct, right? This length won't be wrong, but your direction is going to be totally messed up. So please try not to get caught by that. Okay. Anyways, back to the proper diagram, tip to tail style diagram. We've got our force net going down to the left. So this essentially means that this object is going to get pulled down in this direction. All right, something like that. We'll call that F net. Okay, and we can calculate that. All it is trigonometry. Not even trigonometry. This is Pythagoras theory to solve this. Well, this force net value is the same value we're trying to counteract with this equilibrant idea. Except equilibrant is going to be the force that counteracts this F net value. So what we want is a force that's equal in magnitude, but moving the opposite direction. Right? So if we pull on this with a force up this way, maybe something like that, okay, this angle is going to be 180 degrees from this one. I don't know how I can draw 180 degrees. Just know that this angle is 180 degrees from the force net and pulling at the same strength as the F net, just in the opposite direction. Okay, let us do a little bit of math to solve this, and we will call it done. So if we want to find this F net value, or the equilibrant value, right, we will say we want to use Pythagoras. So F net is going to equal the square root of 30 squared plus 50 squared. And on my sheet, I end up with a value of F net equaling 58 newtons. All right. We can also determine the angle of this, and now once I show you this, I'm going to show you a shortcut, but I want to show you maybe the full length solve here first. Okay, so here is our angle that this is pulling down at, and that to solve it is going to be theta is equal to the inverse tan of 50 newtons over adjacent 30 newtons. Okay, and so theta here works out to be, what do I get? Oh boy, I solved for the complementary angle. So 90 minus 31 would be 60, 59 degrees, I believe. So theta is equal to 59 degrees, and that is south of west. All right, if you drew your triangle like I did in my diagram that I wasn't looking at while I solved this, I did my triangle rather than left and down, I drew it down and to the left. And then my result line was here. This was FNet. And that's acceptable. The only difference is your angle is going to be this complement to the 90 right here. So rather than getting 59 degrees south of west, I had 31 degrees east of south. 31 degrees west of south. Okay. Where was I at? Right. We now have our force net value. Force net, 58 newtons, and it's going down at this angle of 59 degrees south of west. Okay, if we draw this on a plane, let's draw ourselves a little plane down here. Make it nice and straight. Okay, this line is going to be coming out like this at 59 degrees. This is 59 degrees south of west. Well, the line that's 180 degrees from that is coming up this way. It's a little bit crooked, but it'll do the trick. This opposite angle here is going to be 59 degrees. This is 59 degrees north of east. And that, my friends, is what our equilibrant is. So our equilibrant is going to be a force that is equal in magnitude, so 58 newtons, at an angle of 59 degrees north of east. North of east. Right? This angle here, 59 degrees north of east. Now, if that is a system that works for you, you can go ahead and use that system every time. If you'd like to save about only one line of writing. You're not going to save much writing by using the system. But rather than finding this angle here and then finding the complement of it, we can solve for this angle here. Because this angle here is the angle that our force EQ is going to be moving up at. Right? So this angle, if we solved what would this be? If this was our theta, we would do inverse tan again, but it would be inverse tan of 30 over 50, which is going to give you 31 degrees, and this will be 31 degrees east of north. These numbers look different, but if you look on it on this plane here, 59, the complement angle here, is 31 degrees. So all we'd be doing is solving for this complement angle. It tells us the same direction. That answer is just as good. All right. If that system is something you'd prefer to go to, go for it. But either way, it'll get you to the right place.